Now we have already defined the material properties, section properties, and diaphragms. We have already defined the load patterns for the static earthquake, and we have already defined the load cases also and load combinations also. We can define the mass source also here. So for the mass source, what we can do is that we can enter the specified load patterns and dead load. Live load, we can reduce it to 0.5. And after that, SIDL, we can take it as 1, although it is empty and doesn't matter. So we can left click on OK and then again left click on OK. So after that, we can go to the analyze and check model option. We can select all the options, left click on OK to see that whether there is any error in the modeling. So model has been checked and no warning messages were generated. So we can go to the analyze and we can go to the run analysis option. So here we can see the deformation pattern also. So obviously the deformation is maximum at the center and getting a little bit lower at the edges. So we can go to the display and deform shape. Now we can go to the combo and in here we can click on let us say one time dead load plus live load plus SIDL. Click on apply. So we can see that under the case of dead load and live load, the maximum deflection at the center is approximately 10.357 mm only. So after that, we can go to the display and we can go to the show tables option. So in here, we can check the earthquake that has been applied on the model. So we can go to the load pattern definition and analysis result, structure output. Yeah, in here we can see the load pattern definition autoseismic AS41002020 2007. We can switch off all the remaining tables. Click on OK. In here we can see that the site class has been taken as C, KP1, Z as 0.1, SPN 0.7, ductility factor as 2. Period used we can see here at that is approximately 0.389. Coefficient that is used is 0.123 and weight that was seismic weight is 484. So the base shear that is applied is approximately 59.924 kilonewton. Now we can go to the display and deform shape, and here we can see the mode shapes also if required. Although we don't need to do the dynamic analysis, but just as an understanding, here we can see that this is the first fundamental mode. And if we want to see the second fundamental mode, that is somewhat of a, we can say, linear and somewhat of a rotational. And if we want to see the time period here we can see the time period is 0.955 against the 0.389 that has been taken. So we can see that the time period that has been taken is less, so the earthquake force that has been applied is on the conservative side only. So after that we can go to the design, steel frame design and view revised preference. So in here we can go on AS41002020. The steel type is basically hot rolled except for the purlins that are coming on the top. These are the deformation limit that is 360 and 240. And we can left click on OK. So after that we can go to the design, steel frame design and click on start design check. We don't need to ignore the purlin design because that they are already done as per the manual. So we can ignore these, we can say the warning that they are failing in the design. Or what we can do is that we can go to the select and properties and frame section. We can select the C200 1.9, select and close. We can again go to the select and invert selection. So we can click on view selected objects only or show selected objects only. So in here we have just simply switched off the rest of the purlins. So in here we can see that even if with a very small section of 150 by 150 by 6, they are comfortably passing in the design. There's one more thing that we do need to do. We do need to go to steel frame design and select design combinations. In here we do need to ignore these load combinations that are automatically generated. So we can go to the define load combination and then just simply delete these load combinations. Click on OK. We can again go to the design, steel frame design, and select design combinations. In here, select the strength design load combinations. And for the deflection, we can just simply select the serviceability load combinations. Click on OK, and then again perform the steel frame design by clicking on this option here. Basically, we don't need to deselect any kind of member, and then additionally we can go to the Control W and switch off the floors option. We can go by selecting the floors, click on apply and close. Now we only have this these members here. We can switch off the grids also, and if required we can just simply switch off the horizon also by pressing Ctrl W and deselecting the horizon and apply. So now the design is like simple and clear to us. So in here we can see that now the members, if we're talking about this particular beam, there are 360 UB and 44.7. This ratio is like quite good, 0.881. So there's no as such need for optimization, further reduction in the sizes. And if you're talking about the deflection here, the deflection is also like 0.451. And if we click on the strength overrides and if we go to the details option here, the detailed analysis can be seen from this particular window. So we can maximize this. So here we can see that the load combination that is governing is 1.2 times dead load plus 1.5 times live load. And in here these are the different like utilizations. So this is the actual load utilization, that is only 0.002, and the bending moment along the major axis, that is 0.878. So if you want to see the values of the bending moment, so these are the flexural capacities. And for the major bending moment here we can see that the MB value, that is approximately 232 kN meter, and the moment that is coming is approximately 184 kilonewton meter. Or what we can do is that we can click on the overrides also, and here also we can see the like major bending moment capacity. So 232 value that we were saying is without the phi, that is 0.9. So without the strength reduction factor. So with strength reduction factor, the capacity comes out to be 208.87, and the bending moment that is coming is approximately 183. So we are on the safer side. So similarly, we can see the ratio here also. So here also it is 0.881, and obviously with the same section, the bending moment capacity shall also be same, that is 208 kilonewton meter. Now if we click on this particular member here, that is 360 UB 44.7. Now you must be wondering why this is green and why this is blue, because in here we are having a cantilever also projected on the outer side, but in here we are not having any kind of cantilever. So if required, we can do the optimization for this member, that is instead of 360 UB 44.7, we can have a lower size also, that is 310 UB 32. So with that the ratio like becomes quite comfortable, that is 0.513. Or if we do not have any section size lower than this, so we can click on 310 UB 32, and the same like access can be done here also. That is instead of like 360 UB, we can have 310 UB. So again ratio is 0.513. So the same can be checked here also. That is for 360 UB 44.7. If we go with the lesser size, that is 310 UB 32, we can see that now it is failing in the design. We do need to never have a ratio higher than 0.95. 0.95 is the maximum value. So we should not proceed with 0.99. So this is also safe, this is also safe, and this is also safe. Now if you want to see the like behavior of 150 by 150 by 6, so if you want to see the actual load capacity, that is quite high, that is 759 kilonewton, that is very high capacity, and major and minor bending moment capacities are 56 kilonewton meter, and major and minor shear capacities are 340 kilonewton meter. You do need to notice here that the bending moment capacity and shear capacities for both the axes are exactly same. So that is the advantage of selection of the box section. Like in I section, we do have a different properties for the 2 and 3 axis, but for the box section, we do have the same properties for both the axes. So we can left click on OK, and if required, we can further reduce the size from 150 by 150 to 100 by 100 also. Now, the second thing is that right now we do not need to unlock the model, because otherwise what will happen is that the section sizes that has been modified here, like we have done the reduction from 360 to 310 here, that shall again come back to the earlier size. So again run the analysis here, and then after that you can unlock the model to further reduce the sizes of these columns here. And one of the advantage of the like having a box section here is that the lateral deformation is also not that high. We shall also check the lateral deformation of that after this analysis. Unlike by selecting the I sections where we were having a very high lateral deflection with or without bracing, but in here we do not have a very high lateral deflection with bracing. We can go to the display, deform shape, and in here we can select the case or combo as one time dead load plus ELX plus 0.3 ELY. Click on apply, and in here we can see the deformation here is approximately 16.7 mm. So what we can do is that we can just simply select on the default view options, apply, click on the 3D view, and then just select Control Shift and A option on your keyboard. Or we can do is that we can click on show all objects. So now the structure has come to default here, and we have already done the analysis. We can just simply unlock the model, and we can go to the define section properties and frame section here. So instead of 150 by 150 by 6, we can have a further reduction in size. So we can select this box section properties here, and instead of AS14, we can select the Australian or New Zealand sizes. For steel tubes, we do have 100 by 100 section also. So we do have 100 by 100 by 5, and we do have 125 by 125 by 5. So we can left click on OK. Why I'm targeting for at least minimum 5 mm thickness is because for a 5 mm section we can have maximum 4 mm thickness of the welding. So by selecting a very thin sizes, we are not okay with the welding at that particular junction. So like for 3 mm section we cannot do a welding more than 2.5 mm. Similarly, for a 5 mm section we cannot do welding more than 4 mm. So that is why at least we do have some minimum section sizes for the thickness for the connection part also. So what we can do is that we can just simply rotate this model, select all the column sizes here, go to the assign, frame and section properties, and in here we can select 125 by 125 by 5. Again run the analysis option here. So again go to the steel frame design and start design check. So in here now we can see that all the ratios are in yellow. So it is around 0.773, and they are governing in the earthquake also. So here also it is approximately 0.766. Let us say if we further reduce it to 100 by 100 by 5, now we can see that now it is failing in the design. So the minimum section sizes that is required is 125 by 125 by 5. And in case if you're not okay with even 4 mm weld, because frankly I'm not okay with 4 mm weld, I do suggest that minimum we should have a 6 mm or 5 mm weld. So that is why the minimum thickness that I recommend in my projects is at least 6 mm thickness. So what we can do is that we can increase the thickness of the section, that is 125 by 125 by 5 to 125 by 125 by 6 also. So here we can see that it is approximately 5 mm thickness. So we can left click on import new properties, again do the same exercise, that is box section here, Australia, New Zealand steel tube, and instead of 125 by 125 by 5, we can select 125 by 125 by 6 mm section. So again left click on OK, rotate the section, select all the columns, go to the assign, frame and section property. Instead of 125 by 125 by 5, we can assign 125 by 125 by 6. Again run the analysis and see the difference in the results. So now we have already analyzed the purlins part, we have only analyzed the basic moment frame part also, and we have ensured also that the columns that we are having, they are also safe for the loading that has been considered. So just with we can say 1 mm thickness, we have directly increased the ratio here. So it is coming only 0.5 here. In here it is coming approximately 0.665. Earlier they were in the range of 0.7 to 0.8. So that is how the thickness, can be increased or decreased. And in here you can see that now this ratio is coming quite high. That is 0.905. So that is a basic, structural analysis. That is by reducing the column sizes, we are not ensuring much stiffness to the beams. So that is why much bending moment is, because this is a moment resisting frame. So higher bending moment is coming on the beam instead of the column, because ultimately the stiffness plays a role. So if we are increasing the size of this column, the bending moment is like, because that is a basic moment distribution diagram. So the moment decrease by doing that. So I hope the system is now clear to you. We have already, checked the deformation also, deformation patterns also. So the maximum deformation that is coming is approximately 11 mm. So that is quite manageable when we're talking about the steel structure, and that should be within the limit, obviously. So we have already checked when we were doing the design of this particular steel beam here. So under the deflection parameters, we can see that it is coming 0.4458. So we can, when we are clicking on the details option here, in here we can see that the deflection that is coming here, deflection limit is approximately, we can say 9.4. Deflection that is coming is approximately 9.4 and limit is 25 mm. And in here we can see that under the case of the dead load, it is 1.7. Under the case of the live load, it is 7.6. So 7.6 plus 1.7 is 9.4. And allowable deflection is 25 mm, because the length of the member has been divided by the allowable deflection. So that ratio is coming as 0.458. So that is also quite okay with us. So the structure that we are designing is safe in the strength design, that is safe in the serviceability design also.